guys, welcome back. This is going to be the 8.8 instructional video. And what we're going to discuss in this section, our final section of chapter 8, is a topic known as exponential growth and decay. Now, before we jump totally into this, you are going to learn in exponential growth and decay a variation of the formula of the general exponential function. If in this video, if you want to know where this formula comes from, there's a problem that I have posted in another online instructional video called the Florida problem. It deals with Florida's population that will illustrate a lot of items as to where this formula comes from. So if you are a curious person, if you're someone who really to understand something you need to go why, I would encourage you to pause this video, go watch the 8.8 introduction or the theory. I can't remember the title off the back of my head, but it'll say the Florida problem. Go ahead, watch that video. It'll introduce you to the concept of exponential growth and kind of where our formula comes from. Okay, so what are we going to talk about? Well, I've already kind of spoiled the theme, so to speak. We're going to talk about exponential growth, but in order to do that, I think it's best if we have a brief review of what we covered in 8.7. In 8.7, we introduced the idea of exponential functions. So 8.7, we introduced the idea of exponential functions. And what are exponential functions? Okay, well, they're functions that grow or decline or what have you exponentially, okay? No longer, and you saw this with the penny problem in 8.7, no longer are you increasing by a set amount, right? That would be the getting paid $100,000 every day, but rather you are increasing by a multiple, right? We're doubling, we're tripling, okay? Multiplication, repeated multiplication is occurring as opposed to repeated addition, okay? And what we saw in that penny problem is while it may take a slow start for repeated multiplication, almost always over time, if you repeat multiplication as opposed to repeating addition, even if the addition has a high initial value, repeating multiplication will always pass it, okay? What was our general exponential function or the general setup? Well, it was y equals a times b to the x. Remember, y was your total or your result, okay? A was your initial amount, your starting value. B was your rate of change. And X was not your time, but rather the number of times your rate of change occurs. And you saw that in number 9 in your 8.7 homework, right? Where we were doubling every 13 years over a 52-year period. I'm not going to plug in 52 or 13. Rather, in my x value, I'm going to put 4 because how many times do we double? Well, if we double every 13 years and the total time spans 52 years, we would double 4 times because 4 13-year periods would pass. Now, we not only discussed the general exponential formula, but I believe it was in the second part of the 8.7 instructional videos, we talked about some requirements here. Specifically, a cannot be any number. Rather, a cannot be 0. Okay? Your a value cannot be 0. And this was an idea we introduced in that second part of the 8.7 instructional video. And why can a not be 0? Because your function would no longer be an exponential function. It would be a linear function. If we put 0 in for a, 0 times anything is 0, so you just end up with y equals 0. Again, y equals 0 creates a horizontal line. That would be a linear function, not an exponential. In addition, our b value must be greater than 0, and our b value cannot equal 1. Our b value must be greater than 0, and it cannot equal 1. Okay? If our b value is less than 0, you are not going to have that exponential look to it. You're not going to have an exponential function. What you're going to do is just bounce all across the axes if your b is a negative value. If b is 1, again, you are going to get a line. 1 to any power is just 1, so you would have your initial value times 1, so you would really just end up with y equals your initial value, and in that case, you would just have a line. So bottom line, we have these. This is our general exponential function setup. These are the requirements. X can be any real number. I'm not going to write that down because you all have not learned what imaginary numbers are yet. And the thing we concluded with is we looked at 4 different graphs. Okay, the graph of every exponential function, if it meets all those requirements, will fall into one of 2 categories. It might be steeper, it might be a little shallower, but broadly speaking, every graph will fit one of these 2 categories. It will look like this, or this. Oh, I'm sorry, threw that in the wrong spot. It'll look like this, or it'll look like this, or it will look like this, or it will look like this. Okay? And again, we set some categories here. For this left column, A is positive. If your A value, let me get it to line up here. If your A value, your initial amount is positive, if your A value is positive, then your exponential function will be above the x-axis. But if your A value is negative, it will be below the x-axis. Okay? If your B value is bigger than 1, if your B value is bigger than 1, then we can see in this top row here that we are going to be approaching the x-axis when we have negative x values, but as our x value gets bigger, we will increase or decrease vertically on the right side of the graph. And the opposite is true if we look at our bottom row. This is where B is in between 1 and 0. It's less than 1, but it's bigger than 0. Okay, it's like 1/2, 1/3, etc. If your rate of change is that, then on your low x values, your negative x values, you are going to be shooting up vertically or shooting down vertically on when you have negative x values, but as you get into the positive x values, you are going to approach the x-axis. And so we looked at this chart. Again, this is a brief overview of 8.7. Obviously, we went forward and solved some problems. But the million-dollar question is, why have I spent 5 minutes or so bringing this up? Because 8.7 gets a broad view, a broad introduction to exponential functions, and then 8.8, which that theme is exponential growth or decay, hones in on a specific type of exponential function. And what it's going to hone in on are these 2 situations, okay? We're really going to focus with our A value being positive, okay? And we're going to explore what's called exponential growth and decay. And you can see here, you can probably imagine which is which. Here we have what's called exponential growth, and down here we have what's called exponential decay. Okay, it's where you start with a positive A value, and if your A value as x goes, or if you're with a positive A value, if we have a rate of change bigger than 1, as x increases, our value is going to increase dramatically. This is like when we're doubling, we're tripling, we're quadrupling, things like that. Or you're going to have what's called exponential decay, where your A value is still positive, but your overall amount is decreasing as x decreases. This would be like if I cut something in half, right? If I had a bunch of stuff and I just kept reducing by cutting in half over and over and over again, right? So 8.8, again, the broad theme is going to be what's called exponential growth and decay. And again, what this is this is a focused view on some specific types of exponential functions. It's like we're getting out the magnifying glass and we're looking at a specific part of exponential functions, okay? Now, the good news is for exponential growth and decay, broadly speaking, your formula is still going to remain the same. It is still going to be y equals a times b to the x, okay? But we're going to do some manipulations with our b, our rate of change, depending on what's occurring, okay? But again, just so we understand, what is growth? What is exponential growth? Again, we're required to have a positive a value here. So in all exponential growth and decay, your a value must be bigger than 0. This goes for both growth and decay. Your A value has to be bigger than 0. But what separates growth and decay? It's what's happening with your B value. If your B value is bigger than 1, right, you're doubling, you're tripling, you're quadrupling. Bottom line is X increases, so does your overall value, and it increases exponentially. That is growth. Decay is going to be the opposite. Decay is going to be where we are less than 1. Obviously, we still have to be bigger than 0, but our rate of change is a fraction. We're cutting into half. We're cutting into thirds. Okay, our overall population value, total whatever, is decreasing as X goes on. Okay? And so what do we need to really dig into here? Well, there's a big thing I really want to focus, and it's why I'm making this introductory video before we jump into problems. And it's because students with exponential growth and decay, well, I don't think it's super difficult because it's very similar to 8.7. In fact, it is. It's just a special type. A lot of students tend to struggle with exponential growth and decay. Now, we're going to break this into 2 columns. And there's one part most students are really, really good at. And it's the situation you've heard me describing a lot. We're doubling, we're tripling, we're cutting into thirds, okay? We're dividing by 3, we're cutting into thirds, we're dividing by 2, or multiplying 1/2, okay? Most students are very good at this in solving problems involving exponential growth when there is a solid amount that we are increasing or are decreasing by, decaying by, growing by, and decaying by, okay? And that's because you are going to use the exact same formula that you did in 8.7 when we introduced broadly exponential functions, okay? This is very standard, very simple. Let me give an example. Let's say I have a population of people in Mr. Carterville, and in Mr. Carterville, they start out with 10 people, and the population doubles every year, and we want to find the population 10 years from now, okay? Pretty standard, right? Population is doubling, okay? Population's doubling, industry's booming, population doubles every year, and that goes on for 10 years. So once a year for 10 years, that would mean our rate of change happens 10 times, and so you're going to go ahead and model this situation as 10 times 2 to the 10th, okay? And you go, Mr. Carter, we solved these in 8.7. Yes, you're absolutely correct. I want you to understand that they are a form of growth and decay, right? Why is it specifically growth, not decay? Why is this exponential growth? Your A value is bigger than 0, and you have a B value that's bigger than 1. You are growing exponentially. Mr. Carterville is thriving, okay? Now, let's say maybe the opposite. Maybe all the industry left Mr. Carterville, and all of a sudden, oh no, the population is being cut in half every single year, okay? Maybe we started with 100 people, okay? We started with, or maybe 1,000 would be better. We started with 1,000 people in Mr. Carterville, but then all the industry left, and so every year half the population takes off. Heads to somewhere else. Well, this would be known as exponential decay, but again, your setup's not going to change that much. Your rate of change is just now 1/2. And again, we solve it pretty much the same. Now, most students have a good handle on those situations, but here's where most students struggle. Because exponential growth and decay is not limited to just focusing on nice, neat numbers. We double, we triple, we cut in half. No, that's not very realistic, right? Especially when we're talking population. What if Mr. Carterville is growing by 2% every year? What if it's declining by 5% every year? How do we handle that situation, right? Well, before we handle that situation, I think an intro problem would hopefully help us. Let's say we have a sweatshirt for $30, okay? And the price goes up by 18%. Price goes up by 18%. What's the new price of the sweater? Well, you all have learned this before. You're going to take a calculator and you're going to do 30 times 0.18. You're going to do 30 times 0.18. And when you do that, you get 5.4, and you're going to go, great, 5.4, that's 18% of $30. But we said the price is going up, and so you are going to add 30 to it, okay? And when we add 30 to 5.4, we get 35.4. So what's the new price of the sweater? $35.40. And you go, yeah, I know how to do that, Mr. Carter, okay? And broadly, though, let me describe what you're doing, if I may. What you are doing is you are taking your original amount and you are multiplying it by the percentage. Okay, you turn your percent into a decimal, but you're multiplying by the percentage. But you don't stop there. You don't tell me that, hey, the sweatshirt's $30, price is going up by 18%, new price is $5.40. No, that would be crazy, right? The price is going up. It wouldn't drop to $5.40. No, what the $5.40 is, it is the 30 times the 18. It is 18% of 30. And so what you do is you don't just do your original times your percent, you do your original times your percent, and then you add it to your original, okay? Another concept you've learned is factoring, right? If I have 4 plus 8, I could identify that both of these numbers are divisible by 4. And so what I could do is I could rewrite this with a 4 out front, divide both of these by 4, and I have the same math statement, right? They are both divisible by 4. So if I just write out front, hey, I divided these by 4, here's the 4, and then what was left after I divided, 1 plus 2, I've said the same thing. If you don't believe me, you can multiply this back through, okay? 4 plus 8 is 12. 4 times 1 is 4. 4 plus 2 is 8. 4 plus 8 is 12. But if we apply this logic, and by the way, if that doesn't make sense, come talk to me sometime. This should be something you've learned. By that logic, though, I could do the same with what I'm describing up here. Instead of saying, hey, I'm taking my original plus my original times the percent, I can just do my original and multiply it times 1 plus my percent. In other words, instead of doing 30 plus 30 times 0.18, I could do 30 times 1 plus 0.18, or 30 times 1.18, and get the same thing. And this really gets at the idea of this second situation where we're increasing and decreasing by a specific percent. Now, when we are increasing or decreasing, when we're growing and decaying by a percent amount, the formula I would like you to use is the following. Now, it may look a little different, look a little confusing. This is one of Mr. Carter's creations, okay? But what I want you to do is I want you to compare it to your general exponential function formula, y equals a times b to the x. And when you look at it, while at first may be confusing, you should see some similar features. You still have your initial value. You still have the number of times your rate of change occurs. What just looks a little different is our rate of change, our b. And please do not let me mislead you. This is still your rate of change. This is b. I'm just not writing it as b. Why? Because here's the number one mistake I see students make. In Mr. Carterville, we have, I'll write it down here in red so that you know not to do it. In Mr. Carterville, we've got 100 people, population or towns doing well, start with 100 people, but every year that population's increasing by 10%. Every year that population increases by 10% and 5 years go by. The number one mistake I see from students is they go, y equals 100, because we started with 100 people, we're growing by 10%, and we're growing by 10% every year for 5 years. The problem with this is this guy, which is why I would encourage you when we are working with exponential growth and decay, and you're looking at specific situations where you grow or decrease by a specific percentage, please rewrite your general exponential function and don't write b, but in place of b, write 1 plus or minus the percent. And it's because of the logic I just described with the sweater problem. In the sweater problem, you are not going to increase the price by 18% and just multiply 0.18 times the original and call it a day. By that same logic, you're not going to say the population in Mr. Carterville is going up by 10% and just plug 10% in. You're not going to get the right answer. What's really happening there? What's happening is we have our 100 people, and every year we're growing by 10%. We're growing by 10%, right? Think about it like this. If I just look at the first year, you're not going to say 100 times 0.1. You're not going to say we're growing by 10%. 100 times 0.1 is 10 people. You're not going to say the population went from 100 to 10 people. No, you're going to tell me that the population is 110 people, because you're going to take that 10 and add it to the 100 people that were already there. That's what the effect of this 1 is. The 1 in percent terms is 100%. We are adding 10% to our original amount. Okay? We're adding 10% to our original amount. The long and short of it, if you're like Mr. Carter, the theory is just not making sense. When you are growing or decaying by a specific percentage, please, instead of B, write 1 plus or minus the percent. 1 plus or minus the percent. Okay? This is going to prevent you from messing things up, okay, and getting the wrong answer. Okay? That 1 will account for you, just like in the sweater problem, where you don't just multiply by the original by the percent, but you also add it to the original. That 1 there adds it to the original, whether you're growing or decaying. Okay? Now, the second part of this, it's fairly straightforward, right? In place of B, again, not that this isn't B, this is your rate of change, but in place of B, I'd recommend writing 1 plus or minus a percent. That will be your rate of change. Again, these rate of changes don't always look super nice, right? If I simplified what was in the parentheses here, I would get 100 times 1.1 or 1.10 to the fifth. But again, what that indicates is, hey, the population's growing by 10%. Now, if the population was declining by 10%, instead of the plus symbol, fairly self-explanatory, right? You see the plus or minus here. I simply would use a minus, okay? And again, I think the minus helps it make sense even more, right? You don't just want to say the population's decreasing by 10% and put 0.10 in. No, you're going to do 1 minus 0.10. And really then what it's going to articulate is, if I'm decreasing by 10% every year, I'm only retaining 90% of my population, which you can see when you simplify 1 minus 0.10. So the long and short of this, what you're going to do with exponential growth and decay is it's a special type of the general exponential function. It's the special type where your A value is positive, okay? Your A value is positive. It is growth if your A value is positive and your B value, your rate of change, is bigger than 1. It is decay if your A value is positive and your B value is a fraction between 0 and 1. If in that growth and decay you have a nice, clean, neat number, you're cutting in half, you're doubling, you're tripling, you're going to use just your traditional function, plug your numerical value in for B for the rate of change, your 2, your 3, your 1/3, your 1/2, and get the heck out of there. But if you're increasing or decreasing by a specific percent, be very careful. Do not just plug that percent in for your B value. You must remember that your B value is made up of 1 plus or minus whatever that percent is. To close out this video, I'm going to show a lot more examples in the coming video, okay? But to get your feet wet, to give you a chance to really process, hey, Mr. Carter, am I getting this? You've talked a bunch about the idea behind it. I just want to see if I'm getting it, though. Let's go through one problem together. Since 1985, the daily cost of patient care in community hospitals in the U.S. has increased by 8% per year. In 1985, such hospital costs were an average of $460 per day. What is the estimated cost of daily care in 2000? So how am I going to solve this? Well, first things first, I'm going to determine, hey, this is an exponential situation. How do I know that? Because the cost of daily care isn't increasing consistently per year. It's not going up by $10 every year. It's increasing by 8% per year, indicating we have an exponential situation. So what I'm going to do is I'm going to write out my general exponential formula. And really what this is this is not just a general exponential function situation. This is an exponential growth situation, right? The current cost is at $4.60 per day, or not the current, but in 1985, when we're starting to measure this. In other words, our initial amount is 460, indicating that this is going to be exponential growth or decay because the A value is positive. I also know that it's going to be exponential growth because we're increasing by a specific percent. Now, before I go any further, even though I'm on the brink of solving it, I recognize that I'm increasing not by a set number, like doubling, tripling, halving, but I'm increasing by a percentage, which over here, what I'm going to do is I'm going to rewrite this general exponential function. And instead of b, I'm going to put 1 plus or minus the percent, okay? Because when I'm increasing or decreasing by a specific percent, this is what your b value is. It needs to be added or taken away from 1. So my initial amount is 460. I'm told I'm increasing, so that indicates to me I should use plus. Write 8.1% as a decimal. And then I need to look at my x value. How many times does my rate of change occur? In this case, my rate of change, I want to know what the cost is in 2000. It's increasing 8% per year. How many years go by from 1985 to 2000? Since 1985 is my starting amount, well, 15 years go by, right? I start at 460 in 1985, increases by 8.1% per year. 15 years go by. We're trying to figure out what this is, okay? Again, the big thing, the minute you see we're increasing by a percent, I'd encourage you to rewrite your b value as 1 plus or minus a percent. But make sure in the physical problem, you plug in the decimal. So we could simplify this if we wanted to. You by no means have to, though. Again, we can see that this is exponential growth because our b value is, in fact, bigger than 1. And when I plug this in my calculator and solve, what I end up with is $1,479, and I'll round it to 2 decimals since we're dealing with money, 60 cents. Okay? So interpreting our answer, what do we have here? Well, if in 1985, the average daily cost of patient care is $460, and that amount grows by 8% per year, by the year 2000, we could anticipate it to be an average of $1,479.60. Guys, thanks for being patient. Thanks for watching. Please look to the next installment of the 8.8 video for more examples.